So in the last lecture, we talked about the emerging non-volatile memory, and we stopped at this cross-point array and the write and read scheme. So we first talk about this V/2 scheme, and the idea is to have the selected word line, to have the voltage V, right, and then ground the selected bit line. And then for the other unselected word line or bit lines, then you bias all of them to be half V. So in this case, only the selected cross point will see a full voltage drop V. And then on the same row or the same column, the other cells are half selected. They see half of the voltage, half V. And then the other unselected cells will see zero voltage across that. And there's one more red scheme, which is called V/3 scheme. So in this case, we also bias the selected word line to be V, and then ground the selected bit line to be 0. So still the selected cell will see a full voltage V across that. The difference is that for the other unselected word line, in this case, we apply V/3 to those unselected word lines. And then for the unselected bit lines, like those yellow vertical lines, we apply 2/3 of the V. So here you can check that for all the other cells, you will have V/3 voltage across that. For example, this cell, because this side is V, the other side here is V over 2/3 of the V. So here the voltage drop will be 1/3 of the V. And also for those cells that are not on the selected word line or bit lines, for example, this one, you can check. Also, it has here, in this case, this side is V/3, the other side is 2/3 of the V. So here you have a negative V/3 across that. So you can conclude that for the selected cell, you have voltage V across that, and for all the other unselected cell, you have V/3. And similarly, you can do the reset process by switching the priority of the word and bit lines. So in the, this is for the set, this is the reset. For the bipolar switching, you can switch the voltage for the selected cell to be like 0 and V, and then this case, the unselected word line will be 2/3 of the V, and selected unselected bit lines will be 1/3 of the V. So you can verify that all the other cells will see like V/3. So what are the advantages or disadvantages between the V/3 and V/2? So you will see that V/3 scheme, the maximum voltage of the unselected cell will see V/3. While in the V/2 scheme, the cells along the same row or along the same column will see V/2. So of course, V/3 will have less disturb because you see less voltage drop on the cell, unselected cell. So you have less chance to disturb the state of the device. So it has less write disturbance. But it may consume more power consumption. Because in this case, you can calculate the power consumption of the whole array. Actually, all the cells will have the V/3 across that. I mean, all the cells that are not selected, like those cells, all of them will be leaking. So all of them will consume the current. So the total power of the array might be larger. Because in the previous case, V over 2, you will only have the power consumption along the selected row and selected column because you have V over 2 across that. But for the other cells, like those cells, ideally you will see 0 voltage across that. Therefore, the whole array's power consumption might be less in the V over 2 scheme. So there are trade-offs between the V over 2 and V over 3 scheme. And you have one homework on this kind of V over 2 or V over 3 scheme. And you might see this kind of problem in your final exam as well. And then for the read, you can read the cells along the same word line in parallel. And there are two kinds of sensing method. One is the current sensing, the other is voltage sensing. So for the current sensing, what you can do is to apply the read voltage on the selected word line, and then you ground all the other unselected word lines and also the bit lines. So in this case, you have the read current flow this way. And you can read all the cells, those 3 cells in parallel, assuming that at the end of the bit line, you will have the sense amplifier in the current mode. So you sense this current, and this current will depend on the resistance of the cell, either high resistance state or low resistance state. You have a larger or smaller current. And then you compare with some reference current. Then you can get the sense amp output 1 or 0. And the other scheme is voltage sensing. For the voltage sensing, you will need to ground the selected word line and then pre-charge the bit line to be the read voltage. And then for the unselected word lines, you will also have the read voltage. So ideally, those cells will not contribute current. So here only the current will flow this way, ideally. Then this current will make the voltage here decay because you pre-charge. Right, like the SRAM or DRAM case, you pre-charge the bit line, and then this current will discharge the bit line depending on the resistance, the RC delay of this bit line. And then you can use voltage sense amp to compare the decay rate of the bit line with some predefined threshold voltage. Then you can sense it's 1 or 0. So any questions here? All right, so let's talk about some design considerations for the cross-component array. And here we do have one unique element, that is a selector. So here there are some problems with this cross-component array design. The first one is called the sneak path, and second one is the interconnect resistance. So if you look at this 2x2 mini array, if this is your selected cell, and if you bias some voltage here, bias the voltage on your bit line. So here, if you ground your you bias your word line and ground your bit line, then ideally current will flow this way. But here, if the other bit line is floating, then you will have this kind of sneak path current. Because here still this is higher potential and this is lower potential, the current try to find all the possible ways to sink to the ground. Essentially, this is like a resistor network. When you have like a resistor network, let's say those 4 cells. So this is your main path, and then you may have the sneak path, that is through here, those 3 cells. So you will have this sneak path current, which will interfere with your main current. So this will cause the degradation of your sense margin. If you have so many in the sneak path, this is just 2x2 mini array, but for a reasonable size, like 64 by 64, 128 by 128 array, you may have many of those sneak paths, which will cause the trouble of the sensing. And the other challenge is this wire resistance, the interconnect. So here we show those wire resistance. So those wires are made of metal, and metal has some finite resistivity. And then if you pass current along the wire, then you will cause so-called IR drop, because here you have current flows through this one, and this one has some resistance. So the current multiplied by the resistance essentially have the voltage drop across the interconnect. This might not be a problem for this 2x2 mini array, but if you think about a large array, like a 512 by 512 array, then from the driver, you may have the right driver as the left edge, which provides you, for example, this V right voltage. So that means here is V right voltage. As this current propagates through the long wire, at the end of the wire, it will see many segments of this like IR drop section. At the end of the wire, your voltage will see some drop. This delta V is due to the voltage drop across the wires. So the last cell along the wire line will see less voltage. And if this IR drop is substantial, then the last cell might not be able to be successfully written because you don't have enough voltage. So those are 2 issues for the cross-point array design. And the solution is to introduce this so-called selector device. We don't want the pure resistive network. We want to introduce this kind of switch, 2-terminal switch we call selector, in series with the resistor. So here, for example, this is ideal resistor. You have 2 values, the low resistance state and high resistance state. The I-V, you have 2 slope, you have 2 resistance. These are 2 states of this memory cell. And what you want is to have an ideal switch like this. There's some threshold voltage. And above the threshold voltage, the current will be very large. And below the threshold voltage, the current is almost 0. So it's like an ideal switch with this threshold voltage. 2-terminal device. It's like this 2-terminal device, like on state, you short circuit, and off state, you open the circuit. So if you have this selector ideally connected with the resistor, you have this 1S1R element at each cross point, 1S1R. And then if you combine the I-V of those 1S and 1R, you will get this kind of I-V. Basically, below the threshold voltage, your current is cut off. And only above the threshold voltage, you can differentiate your LRS and HRS, the 2 resistance states. The advantage is that if your V over 2 skin, for example, if your V over 2 skin, this is your V, and somehow if you design carefully, this is not to the scale, but if you design carefully, if your half V is below your threshold voltage, then the half selected cell will be cut off. For example, those cells, because they say half V, right? If the half V is below the threshold, then the circuit basically is open here. You don't have a snake path anymore. for those half selected cells because it's cut off below the threshold. So we want to cut off the sleep path below at the V over 2. If the V over 2 is smaller than your threshold voltage of this selector. So this can minimize the power, and also it can improve the sense margin and also the write margin, reduce the IR drop. Because the IR drop, as we discussed earlier, if you have the write voltage at the edge of the array, as the current propagates through the wire, at each segment you have the IR drop. But here you reduce the I here because you cut off this snake path I, then you minimize the current. At least you reduce the snake path current. Therefore, the IR drop along each segment will also reduce, and then you will have a better write margin as the voltage or the current propagates through the wire. So this is the ideal selector, and in reality, we don't have something like this perfect switch you turn on and off at this voltage. So here are some examples of the real like 1S1R device. So one way to introduce this like selector is to rely on this kind of tunneling current. So if you have the tunneling mechanism, you know the current will exponentially depend on the voltage. So this can be like a bidirectional diode. If you think about the diode, right, the PN junction diode, then you have the voltage, current exponentially depend on the voltage. And in this case, we need a bidirectional diode. And if you have this like exponential I-V, this is in log scale. So that means the current will be exponentially decreased as you decrease the voltage approaching 0. So if you have the characteristic like 1S, and here is like your 1R, again, this is in log scale. So this is how it looks like in log scale. So if you combine the 1S and 1R, then what you will have is this red curve on this plot. Previously, your 1R is this like this dash line, gray dash line, and then you have your 1S, which is the blue one. And then if you combine that in series, then you will get the red curve. So the red curve is what we wish, because here you can see the current is suppressed at the V over 2. So for example, here this is like a zoom in for this green box region. If you look at the zoom in, so here this is this point, like your write voltage, you change from the HRS high resistance state to the low resistance state. So this is your write voltage, and then half of that is around here. So you see the current reduction from this point to this point for the low resistance state is like in this example is about like 20x. You reduce this by 20 times. So this number and this number in terms of current, you reduce by 20 times. So you greatly reduce the current at the half V. Because remember, as we discussed before, for the corresponding array, if this is your cell selected, you have the V across that, the other ones V over 2, right? And you want to suppress the current to those V over 2 cells. So here it says that those V over 2 cells reduce the current by 20 times. This is better than pure resistive network. If you don't have the selector, what would be the current for those unselected cells? Right, if you don't have the selector, you have the V across this one, you have half V across this one. If you don't have the selector, what would be the current? If this current is I, this current will be just half of the I, right? You only reduce by 2x if it's a linear resistor, right? If it's a linear resistor, then of course the current proportional to the voltage. And then if you have halfway across those half selected cell, you have half current. Half current actually is a lot, right? If you consider you have many of those half selected cell. And here with this selector's help, we reduce the current of those half selected cells by 20x instead of 2x, right? In this example. So this is the advantage of this selector. So here we define this nonlinearity ratio N as the current ratio at this V and half V point. And in this example, as we just said, it's now about 20x. This is the definition of the nonlinearity ratio. And of course, the larger the better. And in this example, it's not that great, only 20x reduction. And ideally, you may need like 1,000 if you want to build a large array. You may want 1,000 for the nonlinearity ratio. So here is another example. This one is more like an ideal switch in this example. You see the IV is very abrupt for this selector. So this is around the threshold voltage. In this case, the IV is like a abrupt increase and decrease. So in this case, if you combine the 1S1R, then the final IV will look like the plot on the right. So in this case, it's more perfect. The reason is that here this is like your V, and if this is a half V, you see that the on-off ratio or nonlinearity ratio between those 2 points, you completely cut off the current. So the ratio in this case will be huge. This is in the Norst scale. So this is like 10 to minus 5. And this is like 10 to minus 11. So you get the on-off ratio like 10 to power 6. This is pretty good in this example. You can build a large array because you completely cut off the current on the half selected cell. So any questions here? All right, so here we showcase two kinds of selectors. One is this exponential I-V, the first example. The second one is more like the threshold I-V. You have a very like sharp transition. So here we just showcase the I-V characteristics for the individual resistive elements, the gray one, and then the selector, which is the red one, and the combination of this 1S1R, which is the blue one. And again, you define the for the nonlinearity, you define those 2 points. This is like V and half V. So you look at what is the ratio for the low resonance state. We care about the low resonance state. The reason is that low resonance state will contribute more current. So we care about how much you suppress the current for the low resonance state. And you can look at the ratio between those 2 points. So in the research community, actually there are various selector devices developed, and we can simply have this category. The first one is this threshold I-V. You have very abrupt turn on. And second one is the exponential I-V. So you have a gradual turn on in terms of I-V. And this rectifying I-V is like a unidirectional, like the diode. In the conventional diode, it's also exponential, but this one is like only in one direction. So let's say it's like this. And this exponential I-V is bidirectional. If this is 0 voltage, you can turn on the selector in both directions. But for the rectifying I-V, if this is 0 voltage in the negative side, then the current is almost 0. This is like your conventional diode. And there are different kinds of physical mechanisms to give this kind of I-V characteristics. And we will discuss some of them in the next. So for the exponential I-V, you can rely on this kind of tunneling current mechanism. So think about the FN tunneling you did have before. So basically you have to pass this kind of barrier in the band diagram. So at low voltage, the electrons will see a thick barrier made of oxide. And then the current will be small. At high voltage, because the band is bent by the high voltage, then the electrons, let's say, I should say the electron is from the other side. So electrons will see a thick barrier, but at high voltage, because this is tilted, so electrons only need to pass this very thin barrier. Then the current will exponentially increase. So here on the right hand side, we show one I-V characteristic of this bidirectional exponential I-V based selector. So you see here, if this is your V, this is your half V, then you get the nonlinearity ratio about 10 to the power 4 in this case. And also we care about the current density at the on state. So how much current you can pass given the unit area. So here if your area is 1 centimeter square, you need to pass like 1 milliamp, 1 megaamp. This is 10 to the power 6. And the other mechanism for the threshold switching is called this OTS, Ovonic threshold switch. This one is similar as a phase change memory, but without the phase change. So here the hypothesis is that in the off state, you have those electrons trapped, and in the on state, the electrons are detrapped. So in the on state, you can pass a large current. And actually, the mechanism of this device is still under research. It's not exactly clear, but this material, based on the phase change material, does show this kind of a threshold switching. So you have a very abrupt switching. And sometimes people use the current to drive the testing. If you do the current driving in the testing, you basically continuous ramp up the current. You will see a snapback of the voltage. That is the trigger point, the threshold voltage point. If you bias the current, you will see a snapback of the voltage. So if you drive the voltage, this is how you look at the current. It's something like this. If you do the switching, I and V, log scale. But if you drive the current, because current will be continuous, so then you will see this S-shape. S-shape behavior. If you drive the current, that means from the equipment, your current is continuous. Then you will see the continuous current, but you will see a snapback of the voltage when you sense the voltage. So the OTS is important because this is used in commercial product already, like Intel's 3D point memory actually uses OTS as the selector. And there are other mechanisms to do the threshold switching. This one is called the Insulator-Metal transition, and mostly in like VO2 and NBO2 devices. So this device will have some crystal structure change at given threshold voltage, and then it will change from a metallic state, insulating state to a metallic state. So here you see the trigger of the switching. This is like the threshold voltage. But the on-off ratio is pretty small in this case, only like maybe 50x. So this is not very good for large arrays. And there's another like selector based on the conductive bridge random access memory. So in this case, the idea is to have a very weak filament in the oxide. For example, here you drive the saver into the half-lane oxide, and then if the filament is very weak, after the voltage is removed, then the filament will dissolve by itself. So that means here, if you apply voltage, then you drive the saver in, then you make the mechanic conduction, then the current will jump, and after you remove the voltage, this filament spontaneously dissolves. Then you return to the off state. So you can get this very abrupt I-V switching. So I don't require the details of the mechanisms of each of those individual devices, but what you need to understand is the general shape of the selector. Like the I-V, you have the exponential I-V or the threshold I-V. And this table just summarizes the reported selector prototypes from the literature. And they have different voltage range and current drivability and the nonlinearity ratio. And we do wish the nonlinearity ratio to be larger than like 1000 10 to the power 3. And also endurance, how many cycles you can switch the selector. This is also important because every time when you read, you will turn on the selector. So the endurance needs to be high enough to support the read for many cycles. And any questions? Okay, so the other problem is this IR drop, especially when the wire width becomes smaller, or with your scaling of the F, the technology load, the resistivity of the wire will exponentially increase. So here we show the width of the wire, and then here is the resistance per junction, that means per segment, the resistance RJ. This is the resistance per segment. So if the width is below like 20 nanometer, then the resistance will exponentially increase. The reason is due to this surface scattering. So here, if you think this is your copper wire, and the electrons will pass through the metal, but the electrons will be bounced back by the surface. So this is called the surface scattering. And also the copper will have the green boundary. It's not a uniform metal. There are like local greens. So all those boundary and the surface will slow down the electron. That means resistance, right? So here as you scale, make this volume smaller, then the surface to volume ratio will increase, right? As you scale the technology node, the electrons will see more surface than the center. So that means the resistivity will go up. So this is a problem with the scaled interconnect. The resistivity of the copper wire will go up. That means the resistance or the IR drop problem will further increase with the scaling. So here you have to consider all the wire resistance into the netlist if you want to study this problem. And I will skip the details. But here what we care about is the write margin. The write margin is defined as the last cell along the wire line. The actual voltage drop we call V access. The actual voltage drop on the last cell versus or divided by the initial voltage, the write voltage you apply from the edge of the array, because here is like your driver. Due to those IR drop many segments, then you will see smaller resistance, a smaller voltage as on the last cell. Of course, if you want to solve this accurately, you have to consider all the sneak paths in this netlist. So it's very difficult to do hand calculation if you want to do it accurately. That's why you have to run the SPICE simulation and then run the netlist, and then it can solve the current pattern for you. So here the worst case is that all the cells are in the on state or the low resistance state, because that will contribute to largest current in the array. So this will have the worst case pattern for the voltage access. And then for the read operation, what you care about would be the current. If you are doing current sensing, you care about the current range when you sense the on state and off state. So here I just show the simulation results using the SPICE simulator. You can build the netlist like a different array size, 64 by 64 up to like 1000 by 1000. And then here what we vary is the nonlinearity ratio n of the selector. If you don't have the selector, then this will be linear resistor. It's a pure resistor network. If you have that, you see the voltage access, like the voltage access of the last cell versus your initial write voltage as a function of this array size will quickly degrade because of the IR drop and the sneak path. So you have to make the nonlinearity ratio like 1000 to maintain the voltage access even for the last cell of the array. And a rough guideline is your nonlinearity number should be at least similar to the array size. If you have a 1000 by 1000 array, then your nonlinearity ratio should be above 1000. This is a rough guideline. And also because you have the selector, you can reduce the power of the whole array because you cut off those sneak paths. So you see that with this 1000 nonlinearity ratio, then the power consumption reduce like exponentially from like a few milliwatt to 100 milliwatt, 100 microwatt. So this is the benefit of the selector with good nonlinearity or large nonlinearity. You can maintain the write margin and also reduce the write power. Okay, so a quick summary. So we talk about the sneak path, which is undesired, and then the nonlinearity in the I-V will help to inhibit or suppress the sneak path, and wire resistance will cause the voltage drop, IR drop. So here we do need the selector with large nonlinearity. And also if the memory cell resistance is higher, then it will help. Because what you care about is the voltage. If you consider the simplest voltage divider, right, for your last memory cell. This is your resistance of your memory, and this is your resistance of your wire. So what you care about here, if this is your voltage access, if you think about there is another R wire for the bit line. If you ignore the link path, if you only look at the main path, then you can quickly get the V access is like R memory divided by the total, which is R memory plus 2 of this R wire, and then times your V right. So here is a simple voltage divider. Basically, you want the cell resistance to dominate much larger than the wire resistance to maintain the right margin. You don't want the voltage drop on the wire, you want the voltage drop on the cell. I believe you have some homework on this as well. All right, so then the last topic for today will be the 3D exponent. So this is a commercialized technology first invented by Intel and Micron jointly back in 2015. So they really make this exponent array and make it a 2-stack. So they call it 3D exponent. And in this case, they have 2 layer, and the middle is the like shared bit line. And then on the bottom you have the word line 1, and on the top you have the word line 2. And here each cross point you have this 1S, 1R. 1S and 1R. So this is a commercialized technology, and actually you can buy it from the market today. And then after Intel and Micron announced this 3D exponent technology for their high-end SSD application, but they didn't disclose the details of the technology. So there are many questions about what is inside this exponent technology. So there are a list of questions. I don't want to read one by one. So basically, then this tech insight, which we introduced earlier, is a reverse engineering company. So they bought the chip from Intel and Micron, and then just do the reverse engineering and try to figure out what's inside. So this is a report from the tech insight after they dig into the chip. So here, this chip is like 16 gigabytes in the memory capacity, and the array efficiency is pretty high, and the memory density is about 0.6 gigabit per millimeter square. And there are details in this table. So basically, they buy this like SSD, high-end SSD, they call it Opton by Intel, and then they get the chip out, and then cut that, and then examine what's inside. And here are some details. For example, this is the die size, and what else? So this is important. The bit line pitch and word line pitch about 40 nanometer. So that means the wire to wire, the cross point array, the wire to wire pitch is about 40 nanometer. And then half pitch is about F. So F is about 20 nanometer in this case. And here are some cross-sectional view after you cut the chip. So this is the cross-sectional view under the microscope. And this is top view, I believe. So the top view, of course, this is the memory array region, and then you have the peripheral circuits like row decoder, sense amp, and so on. And then if you cut the cross-sectional view, you will see this kind of cross-sectional view. And then they examined the material for the 1S1R. So the element map tells that the R is a phase-changing memory, and it's a GST-based phase-changing memory. And then the selector is this OTS selector. And the composition involves like this selenide, germanium, selenium, germanium, silicon, arsenic as well. And I believe there are some zoom-in picture here. So if you really look at the two stack of the cross-section here, you see the two stack. In the middle is a shared bitline. This is a shared bitline. And then here is like your VLAN 1 and VLAN 2. So here this is the cell, and it's 1S1R. And if you look at the composition, this is GST, and the selector is this SEASGE silicon. And the rough composition is showing here. Those subscripts. Of course, Intel and Micron didn't announce those exact composition, but this is from the reverse engineering reports. And then here, if we compare the exponent with DRAM, you will see that it has much higher density per millimeter square. Let's say the gigabit per millimeter square. So this Intel Optane exponent technology give you like 0.6 gigabit per millimeter square. And then the like 20 nanometer DRAM back in 2015, then it's much lower in terms of density. It's about this 0.1 gigabit per millimeter square. So certainly this one has higher density than the DRAM. But if you compare with the 3D NAND flash at that time it's typically like 32 layer or 48 layer NAND flash. So here the exponent has lower density, gigabit per millimeter square, than the NAND flash. So that's why it's used for the storage class memory. So if you recall the hierarchy, DRAM is here, your SSD is here. In between, we have this storage class memory. And this exponent is a fit with this storage class memory, because the density is in between the DRAM and the SSD. And it's faster than the normal SSD, because the phase-changing memory can read and write in like 100 nanoseconds. But the SSD, you know, the NAND flash, the latency is like tens of microseconds. And this is the first generation 3D exponent. And here are more details in terms of the latency, like hundreds of nanoseconds for read and write. So it's faster than the NAND flash. And one chip is like 128 gigabits, which is 16 gigabytes. And this is like a 3D view of the chip under the microscope. So here, those are the cross-point memory array layers above the CMOS. The CMOS peripheral circuit is hidden underneath. So this is like the NAND flash CMOS under array. So this is array. And CMOS is under the array. And Intel uses this for the Optane memory. And this is like high-end SSD. The application is a high-end SSD. And Micron also introduced their X100 SSD based on the 3D Exponent. And the application again will be the high-end SSD, a fast, high-performance SSD. And Intel continues the development for the second generation. I think last year they reported a 4-layer 3D Exponent. Previously, we only have those 2 layers. Now they stack 2 more layers. So in total, they have 4 layers. But Micron announced they stopped the production of the 3D Exponent last year. So now only Intel is continuing the effort, and Micron gave up because the market is not so great, I believe. And the competition for the 3D Exponent is like a high-end NAND flash. So if NAND flash you don't go for the high density, you can make like it fast by the single level cell operation. If you optimize well, then you can get also microseconds read speed. For example, Samsung introduced the Z-NAND product to compete with the 3D Exponent for the high-end SSD. So you trade off the density versus the speed in the NAND flash, so you can somehow get into microsecond read speed. Alright, so I think that's all for today's lecture. We'll stop here.